Formation and true stress strain curve. We'll discuss basic fundamentals of plastic deformation and true stress strain. We have discussed engineering stress strain curve, and let us revise quickly what exactly we have discussed in engineering stress strain curve and what we have to consider while drawing any stress strain curve. There are few things that we have to be careful about. One is because stress is directly proportional to strain within plastic limit or within a proportional limit. So the curve should follow straight line from here to here. Then E is the elastic limit, and if we remove load up to E by loading a member up to E, then it will regain its original shape. There will not be any permanent deformation, and from E to and beyond this we get yield point where sudden plastic deformation is there. Then it stress increases up to U, and then we get this fracture point. And while drawing this stress strain curve, we divide load by original area of the specimen, so that is why it is called as engineering stress, and we take into account original length of the specimen to find out strain. So that is the basic method of calculating engineering stress and engineering strain. Another important aspect, as we know, that within this proportional limit, stress is directly proportional to strain. So it means that the slope of this straight line is basically the elastic constant E, that is modulus of elasticity. As this particular curve is a representative curve for steel, specifically mild steel, that is a ductile material, and we know that if at fracture the strain is greater than 5%, then it is a ductile material. If it is less than 5%, it is a brittle material. So this particular curve is for mild steel, and mild steel is a ductile material, and mild steel means this plateau, that straight portion, that is only we get in mild steel. As we increase the carbon percentage, this plateau size is reduced, and finally we get a small point. So for all other material, this plateau is not part of the stress strain curve. You won't get any specific yield point in all other materials. Another important thing that for mild steel, SYT is approximately half of this SUT. The general range for yield strength is 180 to 240 or 60 megapascal, whereas SUT is approximately 380 to 450 megapascal. So we should be careful that we should have this yield strength approximately 1.5 to 1.75 or up to 2, twice of this SYT. The another most important aspect for stress strain curve is that we should have this value, because capital E, that is modulus of elasticity for mild steel or for steel, is approximately 210 gigapascal, which is 1000 times of the megapascal unit that we use for representing SYT. So it means if we use this slope, then it is approximately if SYT, that is 200, suppose 200 megapascal, and here strain is approximately 0.001, so or 0.002. So in that case, the value of E will be too much. Slope is too high. It means the theta is approximately 90 degree. So this initial portion of this line should be as close as ordinate, that is y-axis. So these are the few things that we have to take care while drawing stress strain diagram. To summarize, this is stress strain diagram for mild steel. and the mild steel is a ductile material, and this is an engineering stress strain diagram. But what happens actually, as we increase load from zero, the length increases, and once the length increases, it means longitudinal strain is there, and longitudinal strain induces lateral strain, and lateral strain reduces the lateral dimension, that is the diameter of the specimen if we are taking a cylindrical specimen. It means that area is reduced once any load is applied. So for subsequent loading, the stress should be calculated for the original area which is reduced, and similarly the strain should be calculated on the instantaneous basis. So for example, if we take some specimen of original length LO, and after increment of load the length changes to L1, and then we further increase the load, length changes to L2, and further increase the load, L2 changes to L3, and then L4, and so on. So we can find out instantaneous value of strain in by adding all instantaneous strain. The strain so obtained is known as true strain. So for a continuous curve, we can have this delta L over L in differential form, and we can integrate this to L naught to LF to get final value of true strain. So this integration gives us the true strain as Ln LF over the natural log LF over L naught. As the material is expected to be material volume expected to be constant, so that how we can find out the relation of true strain in terms of areas, that is natural log of ratio of A naught over AF, where AF is the final area and A naught is the original area. Now we need to find out what is the relation between the true strain and this engineering strain. So for that I need to convert this LF over L naught in engineering strain. So that is why we consider the expression for engineering strain, which gives us LF minus L naught is equal to epsilon L naught, and finally we get LF is equal to L naught epsilon plus 1. So this gives us LF over L naught is equal to epsilon plus 1. So now we can substitute back. So we get the true strain is logarithmic of engineering strain plus 1. So and we can relate this true strain and stress with the help of this expression, where this is nothing but true strain. And these equations relating engineering and true stress strain are valid only up to the limit of uniform deformation, that is up to necking. After this relation is not hold good. Now let us consider what exactly how the material behaves when it is plastically deformed. So this plastic deformation is the breaking of original atomic bonds, movement of atom, and then restoring. For crystalline material, deformation is accomplished by means of process called slip and involves motion of dislocations, metallurgical phenomena. In amorphous materials, plastic deformation takes place by viscous flow mechanism in which atoms slides past one another under applied stress without any directionality. We can relate stress and strain in plastic deformation, that is basically the portion of stress strain diagram between Y to U. Though the plastic deformation start beyond E, but the point of E, that is elastic limit, and Y, they are practically very close to each other, and we use this Y yield point strength in general for all design purposes. So that is why we consider that these both points are coinciding. So This stress strain curve beyond this y between y and u can be described with the help of this relation. Sigma t, that is true strain, true stress, is equal to k epsilon t to the power n, where this t subscript t represents true value, k is strength coefficient, and n is strain hardening exponent. N is 0, is it perfectly plastic solid, and when n is equal to 1 it is elastic solid. For most of the material, this value is zero point 0.1 to 0.5. If I take logarithmic of this equation, I get log sigma t is equal to log k plus n log epsilon t. If I consider that this is log sigma t is y and log epsilon t is x, in that case this equation become y is equal to some constant, because this is a constant value, k is constant value, it is strength coefficient, n is another constant, and then it is x, so it is equivalent to y is equal to m x plus c, some constant value, that is intercept. So it means that it is represented by a line if I consider on ordinate log sigma t and on abscissa log epsilon t. So it means I get this type of curve between point y, that is, this is the yield point. We will be discussing this portion somewhere as after in another lecture, what exactly is happening here, y1, y2, y3, but right now we will be discussing only this, that we have straight line between y and u, because of this relation, or if I plot this two stress strain curve on this log graph. So n is slope of line CD. So slope of this line will be n, that is strain hardening exponent through plastic region. There is another important that is conclusion from this curve, though it is not clearly visible here, but we will be discussing this aspect as well in next lecture. For most of the material where ultimate strength is greater than the nominal stress at fracture, the n is same as the true strain at ultimate strength. It means the strain hardening exponent is equal to the value of true strain at ultimate point. So this is very important aspect that we use in designing so many you can say things and for so many analysis, that we can find out what is the value of strain hardening exponent and through the normal stress, engineering stress strain curve. The another important aspect is how this line is plotted. There are two straight lines. One line is this CD, another line is this AB. AB is the line which is from this is basically below this yield point, and below this yield point we know that stress is directly proportional to strain, and we use this as sigma is equal to E and epsilon. And we also know that the instantaneous value of change in length below this y, that is yield point or elastic limit, is very less as compared to the change in length, instantaneous length beyond this y. So that is why we can say that this engineering stress and engineering strain between origin to y is both are practically equal, because there is very negligible change because of the very less deformation up to this y. So if I take log of this curve, I will get it is natural log of sigma t, and this will be equal to natural log of capital E plus log of natural log of epsilon t. So what does it mean? It means that the slope of this particular line is the coefficient of log epsilon t, and coefficient of log epsilon t is 1. It means that the slope of true stress strain curve on log graph will always be 45 degree, which is this particular angle. So this particular angle will be 45 degree because the coefficient of log sigma t beyond between this origin and elastic limit is 1. So irrespective of the material, there this line will be at 45 degree, no doubt, because of this log ln, where this particular value intersect with this. So this will give us the value of log E, and this intercept will be different for different material, but the slope of this line will always be same, that is 45 degree. Slope of this line will be different for different material, that is represented by value n, which is strain hardening coefficient. And what is the use of strain hardening coefficient in forming that? Let us try to discuss that. Let us have two different material where the n in one material n is equal to a and n is equal to greater than 1. So we use the larger value of n for getting more uniform distribution of strain. That is our main aim in any forming operation, that we want that if I am forming some component or otherwise, that every point should go with same distribution of strain. It should deform uniformly. So that is my main aim. So let us see what is the role that n plays in maintaining the uniform strain distribution throughout a sheet for sheet metal work or this forming operation. So value of n increases, the material resistance to necking increases, and the material can be stressed further before necking starts. So let us try to understand what exactly happens. If let us see, I take some component like this, where this is a notch, so it means the area of cross section at section A and section C is more as compared to the area of cross section at section B. So if area of cross section at section B is less, it means the stress induced at section B will be more. So if I stress this particular, if I apply load on this particular member, then the stress here will be more as compared to A. Let us take one instant at time t is equal to x. The stress induced at point A and C, let us say, is given by this point, and let us take stress at point B reaches this. So let us say somewhere here we have yield point. So this point is below yield point and this point is beyond yield point. So once this point is reached, so now further deformation doesn't need any load. So it means this B point will be elongating without any additional load, and finally it will fracture at some point. So this, it means that this B point will have this much of strain. So this particular figure shows the strain distribution at point A to point C through this B. So it means strain here is 0, it's slightly increasing, and here it is too high and up to the fracture, and then again in other point it is very less. So it means this type of component, with when this n value is 0 means we have straight line, so that is why this B deformation in B is suddenly takes place, and finally it is up to the maximum value of strain that is possible. So it means the strain in this particular such type of for such material, for a component made up of such material where n is equal to 0 will not cannot be deformed with uniform strain. So let us see what happens if you have some another element where the n value, this is not equal to 0, rather it should not be equal to 0, it is greater than 0. So if we have this type of material, so let us say this is the yield point. Even if we have this yield point at time t is equal to x, the stress at point A and C is at any point through section A and C is this, and at B is this. So once load is increased, so stress at point B will increase up to this, and stress at point C will increase up to this, and so on. So it means the strain difference in the strain is will only be maintained by this particular gap. So we'll be having more uniform strain gradient as given by this particular diagram. We have only this much of strain gradient. This will be maintained as we increase the load. So that is the main advantage of strain hardening coefficient. We should have a material for forming process of which the strain hardening coefficient is more. So thank you for watching this video. Thank you very much.